All right, now we're starting again with the recording. For the recording, my apologies. The first bit got cut off because I was asleep. Now we're going to talk about Virial theorem. So, Virial theorem. The book starts with this funny quantity that he calls Q equals the sum of the momentum dot the vector. Man, I totally started in the middle. Let's start at the beginning. Okay, I got a collection of things. Let's call them point masses. Let's call them stars. They could be galaxies in a galaxy cluster. They could be atoms in a gas. Any collection of things doesn't really make any difference. You can do this with whatever system that you want. So in our system, so you can let me say that again. You can generalize this idea to much more complicated systems than just a blob of stars. A blob of stars is relatively complicated, but it doesn't have any weird vector forces or anything. So each one of these stars has a position Ri, a velocity Vi, and a mass Mi. So what we want to say is, we want to say something about these. So the book starts with this quantity Q that's the sum on the momentum P times R. Pi times Ri, where, okay, so of course Pi is Mi Vi. So, but he doesn't really motivate this quantity. It's not really, I don't like starting this way.
What is the symbol next to the P?
This is a sum.
Oh no, on the other side of the P. Oh, okay.
It's a dot. That's a dot product dot.
Oh, okay.
This is kind of non-intuitive. The way I like to think about the Virial equation is it's a spatial averaging of the forces all balancing out. So it's a statistical balancing of the forces when taken as a spatial average. A little more complicated than that, but that's really what we're going to show. So the reason that he's doing it this way is because momenta are immediately related to forces. And Virial theorem is really about force balance. I'm going to start this way. I'm going to start with this quantity I, which is the moment of inertia. How many of you remember moment of inertia? How many of you kind of are real dodgy on moment of inertia? Yeah, very cool. So moment of inertia is like the mass, but for rotating. Right? It's the resistance to changes in the rotational motion about an axis. Does that make sense? Sound familiar? Right. So if I'm going to try to rotate something, I'm going to apply a torque. A torque is R cross F, which is a force at some moment R. And then the torque is the moment of inertia times theta double dot, or alpha, or the acceleration in the angle. This is equivalent to F equals ma, except everything is multiplied by a distance because we're rotating about a point. So you don't have to remember any of that. All you have to remember is what I is. So now I'm going to look at what I dot is. I dot, I'm just going to take one time derivative, and I'm going to keep using the dot notation, but feel free to stop me and make me, like, if you get lost on the dots, stop me.
And what is that derivative with respect to?
Time. Dot is always time. And it's the only one that I ever really use implicitly. Everything else I'll be explicit with what we're taking the derivative with respect to. The time is special. Do you have a question?
I was going to see if you ever use different shapes.
Was that?
If you ever use different shapes for different derivatives. They're going to plot a triangle.
Not in this class.
Triangles already mean so many things.
But yeah, you can use you can definitely use other hats and decorations. But really, I find it As long as if it's anything other than time, I find it best to just be explicit with what you're taking the derivative with respect to, because otherwise it's really easy to get lost. So I dot is going to be what? The sum on I of masses are all constant. So the only thing that changes is R. So this becomes Ri dot. And remember, the R's are vectors. I'm not going to cloud things up by drawing the vector symbols, but keep in mind they're vectors. So the derivative of the moment of inertia is m times Ri dot. And then the second derivative is sum on I. Oh, I'm sorry. Jesus Christ. It's a square. Sorry about that. My copy editor didn't catch it in time. There's a square there. The square is super important because you get zeros all over the place if you don't have this square. Like if I have a system like this, so this is my axis, I have a mass over here, I have a mass over here, this is R, this is minus R. The moment of inertia, the way I wrote it before was 0, because R and R minus R are going to cancel out. R squared. Very important that it's R squared. So the moment of inertia is mr squared. So the first derivative is a 2 comes down and you're left with 2mi ri dot. Okay, so ri squared dot. Now it's important that the dot is outside of the square. The dot is not inside the square. So the derivative of ri squared, the 2 comes down, you're left with an ri dot, and you're left with an ri. Everybody happy with this? This is chain rule. Yeah. If you're not, stop me and I'll back up one minute. So now I'm going to take the second derivative of this. I'm going to move this 2 over here so I get a 1/2. This chalk is now too little. Yellow one, so I'm going to 1/2 I double dot, so that's the second time derivative, equals the sum on I of mi. Okay, I got to product rule this. So it's the derivative of the first times the second. That gives me an ri dot squared. Because this is going to be an ri dot, this is an ri dot. Now the square is on the outside of the dot. Plus ri double dot. So what's ri dot? Velocity. So this is equal to the sum on I of mi vi squared. That is 2 times the kinetic energy. Plus the sum on I of mi ri double dot. So this is a little messier. So this is ri double dot. Acceleration. M times acceleration. Force. So this is ri fi. Alright. So
I'm gonna throw this up so that you can look at it while I do it. I'm going to put this on the display. I think my first verbs were not right. There you go, okay.
this is it. This is all the slide decks are online.
Not all of them are useful, because a lot of the stuff I do on the board, I don't repeat a lot of the stuff. Like I haven't teched up all the notes yet. Okay, so let me change where I'm at. I'll put this up.
Come here. This is what I just said. 1/2 I double dot is twice the kinetic energy times the sum of the number of particles times R times F. I used K here instead of
I, because that made sense to me at the time, but it doesn't make any difference. Okay. Very dirty. F is 1 over R squared. R times F is 1 over R. This is potential energy. Does that make sense? So
in the dirtiest way possible, though don't actually do this, but you can see it like aesthetically, that I've got Fi equals Gm m over r. So Fi times r is equal to G squared m over r, which is just potential energy, right? That's basically what we're gonna do. That's not entirely accurate, but we can make it accurate. Because that's not how force RF is not U. F is the integral, or F is the derivative of U, or the integral. You gotta have an integral there. You can't multiply and get an integral. But because it works like 1 over R, it works out well enough. So when you have forces like this works out great. So in the dumbest thing possible, or the cheesiest derivation possible, I have sum over R times F, which is just U. So I'm left with 1/2 I double dot equals, I'm just gonna write this up later. Okay. 1/2 I double dot equals 2KE plus PE, or U, let's call it U. Alright, so put a pin in that for a second. I'm gonna come back and talk about what that means in a second. I'm gonna do a little bit of gross algebra for a second. Just so that you see how this works.
So
The quantity I have is the sum on I to n of Ri Fi. So Fi is what? This is equal to the sum on I to n of Ri. Sum on J equals 1 to n of G m I m j over Ri minus Rj quantity squared Rij hat. The reason that doing it the way that's on the previous screen isn't right is because the force between two particles is not R, it's the difference between their positions. Now it is R when you're in that frame. So it all kind of works if you wave your hands and don't care about things. But we need to get an Ri minus Rj on the top to actually cancel this Ri minus Rj. And what we're going to use is the fact that the force is symmetric and we're double counting everything. So there's two things in this sum that we get to use. So the first is the fact that we double count. So if I think about this sum, I've got a sum on I and a sum on j. So this is a sum on all the particles. And then for each sum on all the particles, I'm doing another sum on all the particles. Does that make sense? So every time I say I want at this point, for this particle, all of the forces, I gotta add up a contribution from every other particle in the morass. So I can rewrite this. So I'm gonna keep this as F for a little bit. So this is sum on I, sum on J, Ri, Fi, J. So this is now the Ij force between two particles. This is J, this is I goes from 1 to n, and this is J goes from 1 to n. But I can just as easily say that this is equal to I goes from 1 to n, sum on J goes from 1 to n over 2 of Ri Fij plus Ri Fji. So if you think about this sum, so I've got an I index here and a J index here. For each one of these, I've got a term that I add up. So think about this like a matrix. But the top half of the matrix is equivalent to the bottom half of the matrix. And if I do it this way, I just go from 1 to a half of them, but I flip them around and split it up like this. This is like saying 1 equals 1/2 plus 1/2. The only thing I've done here. I've done a little bit of index manipulation to make it actually true, but this is just saying that 1 equals 1/2 plus 1/2. So now the next thing that I'm going to do, so that's this line here. Then the next line is I'm going to use what I know about Newton's laws.
and I know Newton's third law, action and reaction. So Fij is equal to minus Fji. So if I'm on one planet and I look at the other and I'm looking at that force, it's the opposite of being on the other planet looking in the other direction. So now I'm going to pull a stunt. I'm going to expand this for a sec. So this is equal to sum on I, sum on j, up to n over 2 of r I f I j, plus the sum on I to n, sum on j to n over 2, r I f j I. The second one, I can just relabel I and j, or I'm going to swap I and j here. So actually, there's 3 goofy stunts in this. The first is splitting it in half and adding up both halves twice. The second one is saying that Fji is minus, so this is a plus from this stunt, but I'm going to swap Fji with Fij and I get a minus sign because of Newton's third law. So this turns into a minus sign and this turns into Fij. And then I'm going to rebrand, so I can just relabel I goes to j. And this turns into a j, this turns into an I, and this turns into a j. And what I'm left with is here. So I have Fij turns into Fji, and then I swap the indices, so this turns into an I, because I can just relabel the indices. And then I'm left with Fjk as Rj minus Rk, and this is the numerator that I need to actually cancel out the denominator. All right, normally I don't go through that much algebra, but it's kind of hairy, and it's not really right to just cancel out the R. Really, you can just cancel out the R. This works just fine. So sometimes you can wave hands and sometimes you can't. Here, I wanted to make sure that I was explicit with how this sum works. But anyway, so the upshot, where do I going? 1/2 I double dot equals 2ke plus u. This is as true as F equals ma. I didn't do anything that isn't F equals ma here. So this is not approximate, this is a factual statement. I waved my hands maybe when I did that integral, but this proves that doing that, you can do that integral perfectly and it works out just fine. So how do I use this? Because 1/2 I double dot is not something that I know how to measure with a telescope. Neither is ke or u for that matter, but I double dot I really have no idea. So, but what is I double dot? Let's say for a minute I've got a sun going around a planet. And I'm going to average this from 0 to 1 period. Right? So if I just average this sentence over 1 period, then I've got the average kinetic energy and the average potential energy. And the average of I double dot, well, what's that? The average of dt of I double dot, if I integrate this with respect to time, I'm just left with I dot. So I integrate once and I get rid of a dot. Evaluated at the endpoints, this minus this. So this is evaluated at A and B. So this is I dot at A minus I dot at B, but A and B are the same point if I'm evaluating it around 1 period. So this equals 0. So this equals 0, so 2ke plus u equals 0. So if you've got a closed orbit, this thing goes away, and I know that twice the kinetic energy plus the potential energy is a constant. It's 0. Now it doesn't have to be a closed orbit. It just needs to be statistically a closed orbit. This is an average quantity, so I averaged over the whole ensemble of things. So say I've got a globular cluster with 1 million stars in it. I average over all of the stars. As long as the average isn't doing anything, then this side goes away too. So as long as you're looking at closed orbits, or a relaxed system,
then the virial theorem is true. Because it's just as true as with the I double dot, it's just as true as F equals ma. But if you can relax everything, then the forces are all basically balanced, or at least statistically balanced. Then you get twice the kinetic energy plus potential energy is 0. Yeah.
What's a relaxed system?
A relaxed system is something that's statistically not going to change very much.
Okay.
So if I look at a globular cluster of stars, that's 1 million stars in this tight little ball. And those tight little balls stay like that for billions and billions of years. So on average, each star isn't actually on a closed orbit inside the globular cluster. They're all going to wheel around and interact with each other, and maybe there's some binaries, and who knows what's actually going on. So it's not a closed orbit, but it's statistically closed enough. Okay. Anybody have any? Yeah.
As long as it's on a closed orbit or relaxed system, the 2k plus u is 0.
Yeah.
That's
Yeah. Okay. I got 5 minutes left, and I'm going to start with magnitudes. Does anybody have any questions about this? So I didn't put virial theorem on the homework, but make sure you understand this derivation because I wouldn't feel bad putting it on the midterm. Because I don't think it's all that hard. I don't think it's super complicated. So make sure that you understand this thing. Now we'll move on with my least favorite thing in astronomy, the magnitude. That's not entirely, well, yeah, it is. That's entirely true. I'll explain. Okay, so let's start off with the inverse square law. And magnitudes are almost dope. I like half of the magnitude, and the other half of the magnitude is so infuriating that I hate the whole thing. Okay, so let's start off with the inverse square law. So F equals L over 4D squared. I think it's that important. So this equation underpins monster amounts of physics. So what this means is something's spreading out as it expands, but it's basically conserved. There's a lot of things that work like this. So this is the flux. So F is a flux. And it is measured in energy per time, per frequency, per area, per solid angle. So that's the flux. And the luminosity is like that, but you get one extra area less. Because you got this extra d squared, so there's an area. So let's talk about the units for a second. So a flux is stuff going across a surface. So you can have a flux of people across a border. Say this is the United States, you can have a flux of people across the border. That would be, you would measure that in people per second per area of the border. Be a linear perimeter. The flux is not the number of coming in, it's the number per area of coming in, that are coming in. So if I've got a star and I've got a wind coming off of the star, I get a flux of particles. If I draw a surface out here, or just a little surface right here, I get a flux of particles that's in particles per second per area. And that's not everything that's up there. So what I wrote up is that my flux is going to be in ergs. Yeah, what's an erg? Anybody know what an erg is? Okay. I will complain about MKS all the time. Half because I think it's funny, and half because I'm an astronomer. We all use CGS for reasons that I will explain probably at the beginning of the next lecture. An erg is an energy in CGS. CGS is centimeter gram second. So an erg is a gram centimeter squared per second.
because it's like an energy. Oh, per second squared. Sorry. So it's like an energy, mv squared. So an erg is the unit of energy, and it is, let's see, it's a gram times a centimeter squared. How much is a gram? About, it says like 20 bucks. It's like a paper clip.
Great.
Right? So a paper clip doesn't weigh very much. A gram does not weigh very much, right? And a centimeter is not very big. So an erg is like an ant doing a push-up. Really not a lot of energy. But when we're gonna have to have 10 to the 50 of whatever, we can use the little ones. So an erg is a little unit of energy. A photon doesn't have very much energy, so we like to use the little units. A dyne is the unit of force. It's a gram centimeter per second squared, like an acceleration. They show up from time to time. I'm going to talk about ergs all the time because it's the preferred unit. So the flux is going to be in ergs, which is just energy. You could do it in photons too, but then you have to convert photon energy to energy. Ergs per second per area per wavelength, so that's also going to be in centimeters, per steradian. Okay, I know what a steradian is. I do not know what a steradian is. That is great. A steradian is a two-dimensional angle.
Is it?
That's all right, nobody ever does. I always get here and figure everybody's going to raise their hand.
It's because I've worked across the street.
When you need to know it, then you have to learn it. So this is an angle. Here's an area. This two-dimensional thing, right, is a steradian.
Which is an angular area?
It's like an angular area. There are 4 pi steradians in a sphere. So that's the thing that you need to know. There's 4 pi of them, and it's the angular area. So if I'm just looking at the top half of the sphere, then that's 2 pi steradians. If I'm looking at some little window, then I just multiply the angle across by the angle of the other direction across, and I get the number of steradians in that area. Why is that there? Because what I'm trying to ask here is, how much crap do I get in my detector? My detector looks like this. Now, if I make my detector twice as big, I get twice as much stuff. That's what the area gets you. Here's my detector. If I can only see this, if I'm blocked by only seeing a little tiny window of the sky, I'm going to get a much smaller signal than if I'm looking at the whole sky. So this steradian is how much of the sky you can see in angle. Because if you block some off, you block some of the flux off. Okay, I'm going to stop there because I think that anything else is getting deep in the weeds. Let me know if you have any questions.
And I'll talk to you guys on Wednesday.